All right, are we ready? Let's look at some molecular shapes. So we talked about this a little bit last week in the lab, kind of roughly, and I gave you a quick table to use as a shorthand. Now we're going to build it up kind of piece by piece and understand why this happens the way it does. And this is what the model is, VSEPR. It's pronounced Vesper, even though that's not really, should be Viseper or something. That stands for valence shell electron pair repulsion. And the theory is, from this, is that electron pairs want to be as far away from each other as possible. They repel each other. And whether those pairs are in bonds or whether they're not bonding electrons, they want to be as far away from each other as possible. Given that assumption, here are the shapes that molecules take. So this is a theory. This is a model. This is a way to explain why molecules take the shapes that they do, and it doesn't always work. It works very well for some types of structures, as we'll see, and then it breaks down for some other types of structures, as we'll also see. So first, we'll start with the simplest one, the linear structure. So when you have something like BeCl2, and we can make a Lewis structure for this. It looks like this. Those electron pairs are going to want to be as far apart from each other as possible. And when I talk about the electron pairs, we're talking about these two bonds. We can also think of the electron or the atoms as repelling each other as well. But for those two to be as far away from each other as possible, they're going to go to opposite sides of the molecule. And that makes what we call a linear structure, straight across, bond angles of 180 degrees. So this angle, the CL-BeCl bond angle, is here, is 180 degrees. One to the other. And again, the thing that causes that is these electrons wanting to be as far away from each other as possible. All right, moving to the next structure, BF3. Now we drew BF3 in a Lewis structure like this. But that's not the best way for these fluorine atoms or those bonds to be far apart from each other. A better way, a way that allows them to be farther apart, would be like this. To be at the corners, for the fluorines to be at the corners of a triangle. An equilateral triangle. If the boron is in the middle and the fluorines are at the corners, that's as far apart from each other as they can be. And those angles will be 120 degrees. We call it trigonal planar because they're in the same plane. So if let's see if we can find this thing. So here's our structure of BF3. Oops. And you can see that all of those are lined up in the same plane, all those fluorines. So it's kind of a flat molecule. Whoa. And if we distort one, the other ones move away from it. So I guess that's kind of the point of this little app here, is if you try to move one, it's going to repel the other ones, pushing them away until they end up flat again, which is where they want to be. So that allows the fluorines to be as far apart as possible from each other. The first one that gets a little bit tricky for us then is CH4. If we drew a Lewis structure for CH4, we might end up with something like this. But again, that's not as far apart as those hydrogens can get from each other. We looked at this three-dimensional structure as a better description, where one hydrogen is coming out at you and the other one is going back behind. The reason that's a better structure is, according to this model, now those hydrogens can be further apart. Those electron pairs in the bonds can be further apart from each other. And that bond angle is about 110. Now, you'll always see in books that it's reported as 109.5. And it's true that the bond angle in methane is 109.5. But any other molecule that takes this shape is not going to be exactly 109.5. It's going to be a little bit different based on sizes, based on stuff. So I don't know why they report it so specifically when it's really only true for this molecule. I think of tetrahedral as just around 110. So if we look at that, here's what that looks like in 3 dimensions. So if you can kind of see the way we've drawn it, you've got one kind of going up, one hydrogen going up. One going up, one going down to the right, and then one coming out toward you and one going behind. You'll notice the one going out toward you right here and the one going behind are really lined right up in that model. But we draw them kind of like this just to so we don't get confused about missing one. But that's what that 3-dimensional shape looks like. The corners of a tetrahedron. And they kind of repel each other again. It's kind of fun. And that's called tetrahedral. Okay. So why is that better than a square planar structure? What would the bond angles be here if they were actually in a T like that? Or plus shape. What? 90. So you can see that that wider bond angle allows the hydrogens to be farther apart from each other. And that's why it adopts that tetrahedral structure. All right. So if we draw Lewis structures then for each of these, here's how we apply the VSEPR model to determine the geometry. We figure out our Lewis structure, and then we count the number of groups around the atom. So for methane, we've got 4 groups, and they're all hydrogens. We call those electron groups. For nitrogen, we actually often draw our Lewis structure like this, but we count that lone pair as one of the electron groups. So we don't usually draw it this way, but for our purposes right now, we can think about that electron as being kind of an extra bond there, so that we can see that it's a similar group. And then for water, we could do the same thing. Water has 2 lone pairs, so we can think of them also as having 4 electron groups. So their geometry in terms of how the things are distributed around the central atom is tetrahedral. Their shapes are given another name because we can't actually see the lone pairs. The lone pairs are on that central atom. We don't really see them. They do take up that space. Well, we pretend that they take up that space so that we can correctly report or guess the structure. But we have different names for those shapes. And those are trigonal pyramidal and bent, or V-shaped. So let's look at what that looks like in the 3D structure again. If we look at NH3, so you can see that with the lone pair, I wish we could zoom in on this a little bit. Can you see that? With the lone pair, it looks just like methane, right? A tetrahedral structure. But since we don't actually see that lone pair, we have a structure that looks like this, which is actually called trigonal pyramidal. It's like a triangle pyramid. You can see those hydrogens kind of make the bottom of a pyramid going up toward that nitrogen. We'll also talk about in the real structure here. Let's skip those. Let's look at water. And we'll notice that the bond angles in these are actually a little bit different. So if this is called the model structure, we'll show the lone pairs again, with 109.5 perfectly tetrahedral bond angles. But the real structure of NH3 is a little bit different. You'll notice that the bond angles went down to 107.8. What's happening there, and according to this model, is that the electron pair has a little bit of extra repulsion, and it kind of pushes everything else down away from it even a little bit more. If we look at water, we see something similar. So there's water with its electrons in that perfectly tetrahedral model. But since those electrons push down a little bit extra, we actually end up with a smaller bond angle for water of about 104.5. So So that's that extra repulsion from those electrons. And then since we don't see the electrons, we call this shape bent instead of tetrahedral. So the geometry, the bond angles come from tetrahedral, but we call it bent. And there again, it's talking about these different shapes. And whenever we see those lone pairs of electrons, we see this trend, that the lone pairs push a little bit extra on the others, which decreases that angle a bit. All right, so those are structures that we're all pretty familiar with. Let's look now at the bigger structures, which can throw people off a little bit. A trigonal bipyramidal structure is perhaps the most weird or something at this point. We can think about that. PCl5, it's going to be a central phosphorus atom with 5 chlorine atoms around it. And 3 of them are in the same plane like this. And then there's going to be one coming out at you and one going back. So it's like a trigonal planar structure in the middle, and then kind of a linear structure superimposed on it. These are known as the axial bonds, or the axial parts, or constituents, or however you want to call that, the axial things, being on this axis. And the ones around the middle are called equatorial, around the equator, around the middle. And there are 2, so when we say the bond angles, when we talk about the bond angles in a trigonal bipyramidal structure, there are actually 2 different bond angles. The bond angles between the chlorines in that plane are 120, just like in the regular trigonal planar structure. But the bond angles between an axial and an equatorial bond are 90 degrees. So this bond, these bonds here are 120 degrees. These bonds here are 90 degrees. So let's talk about how this one breaks down when we have electron pairs instead. So instead of PCl3, let's look at one that was on the exam, SF4. So we're going to have a central sulfur atom and 4 fluorine atoms. And most people drew this something like this. And when you add all your electron pairs, you find that there is an extra electron pair that has to go on sulfur in the middle. So 4 bonds and 1 electron pair means 5 total electron groups. And that tells us we have a trigonal bipyramidal type electron geometry. So let's draw that. The question immediately becomes, where do we put the electrons? Do we put them on an axial bond, or do we put them on the equatorial bond? What do you think? How would we even make that decision? Let's draw both of them and see what we think. So let's put the electrons in the equatorial bond. And then let's put the electrons on the axial bond. Which structure do you think is better in terms of minimizing repulsions, and why? I'm going to get rid of this one up here because we used that already to get our Lewis structure. Yeah.
The one on the right.
The one on the right is better? Why?
Because if it's in the middle, then it's also affecting the one below
Okay. So it's further away from the one on the bottom. It's got 180 degrees from the one on the bottom on the structure on the right and not on the one on the left. Okay. Other ideas? It's actually the one on the left is the better structure. The reason is because of the total interaction. And the one on the left, we want to minimize these really small, these close interactions. We want things to be as far away as possible from that lone pair. The one on the left, we have 2 fluorines 90 degrees from the lone pair, and then the other 2 are far away at 120 degrees. The one on the right, we actually have 3 that are all at 90 degrees. So that ends up putting them closer to the lone pair. And so this actually ends up being the better structure. The forces, even though the one on the right has a fluorine that's further away, the forces are actually minimized in the one on the left because of the fewer 90-degree interactions. So let's look at those structures. First, we'll look at a PCl5, which is that trigonal bipyramidal. And so you see those 120-degree bond angles around the middle, and then the 90 degrees on top. If we move to SF4, we see, and we can show the lone pairs, that the lone pair ends up on one of those equatorial bonds sticking out the side. And we call this shape Seesaw because if you kind of put it this way, it looks like a seesaw that goes back and forth at the playground. So that's Seesaw shaped. The real structure, once again, has a little bit more repulsion from those electrons. So instead of 90 degrees, we have 87.8 degree. And then instead of 120, we actually have a much smaller interaction here, 101.6, from that electron pushing those other bonds away. All right, so if you're going to take out one more electron, where is it going to come from? I'm sorry, if you're going to add one more lone pair and take out an atom, where are you going to do that? In the structure, I think. Are you going to take the second one off of the equator here, or are you going to take it off of the top here? Off of the axial. Yeah, we're going to take it again off the equator again for the same reason, because that's what will minimize those repulsions. The reason for that now is if we put an electron here, now the lone pairs have 90 degrees between them, and that's way too close. If we put the lone pair over here, the 2 lone pairs have 120 degrees between them, that's better. So an example of that structure might be ClF3, where you see those 2 lone pairs, and then the rest of the atoms there. If we remove those lone pairs, we have the actual shape of the molecule, which we call creatively T-shaped. And once again, we've got a little bit of a change in bond angle from 90. That would be the ideal structure. Those lone pairs push that down a little bit. And so that gets us a T-shaped structure. The electron geometry is still called trigonal bipyramidal. And so that's how, remember we looked at that big table. We can go back and look at it now, and then we'll get to octahedral. When we look at this whole table, if you look at the trigonal bipyramidal section here, you'll notice that all of these are trigonal bipyramidal electron geometry. We have different shapes. If we take one more out for a lone pair, we end up with a linear structure. But if you remember, if you remember the main geometries, and then you just think of taking each atom off and replacing it with a lone pair, then you don't really need to memorize all these different shapes. It's more about what shape do you get when you remove this and leave just an electron behind. So we'll go back up and we'll talk about the final one, which is octahedral. Now, there are larger structures than this. There are things with more than 6 things connected to them. We're not going to get into that in this class. If you go on and take inorganic chemistry, you'll see a little bit of that. An octahedral structure like SF6 has, again, axial and equatorial type bonds, but actually in an octahedral structure, they're all the same. So it's often written like this. We could also use our dash and wedge notation to show that these two are actually coming out at us and those two are going behind. So in the octahedral structure, there's no distinction between the equatorial and the axial bonds. If you rotate it, they're always going to be the same. In trigonal bipyramidal, that's not the case. You can always tell the equatorial from the axial because of the bond angles. But here, you've got 90-degree bond angles everywhere. So they all look the same. Let's look at an example of an octahedral structure, SF6. So 90-degree bond angles, there's our axial. We might call the top our axial, and these are equatorial. But then if I flip this up like this, suddenly we have a new axial and new equatorial, and then they're actually all the same. So you can see 90-degree bond angles all around there. All right. If we remove electrons from here, it doesn't matter where we remove them from because, again, they're all the same. So we remove one electron and we get this. This is known as square pyramidal. So that lone pair is down in that empty space when we removed one. Called square pyramidal because if you imagine this as a pyramid with a square base, like the pyramids in Egypt, that kind of a thing. And then as with all the other ones, the presence of that lone pair ends up pushing the other atoms up a little bit. And so the real structure is not exactly 90 degrees, but is a little bit less. And then if we remove a second one, where do you think the second one is going to get removed from? Yeah, the top, right? If we take it off the top, let's show that lone pair again. We've got one down here. Lone pairs really repel each other a lot, so we want that second lone pair to be as far away as possible, which is going to be up here. Push them away. So that would be something like this. Where we now have the lone pairs on either side, and that's known as square planar, just like trigonal planar. It's like a planar structure where each atom is in the corner of a square, and the central atom is in the middle of the square. If we have more lone pairs, we can get, I don't think they're on here, maybe SO2. Not in this example, but if we have more lone pairs, we can get, we could count that one down as well. I don't think that's possible actually to get more lone pairs on the central atom. So those are the shapes that you need to know, both the electron geometry here and then the molecular geometry. And you should be able to derive the molecular geometry from the electron geometry. So yes, you have to memorize the names. That's just a memorization thing. But you should be able to at least figure it out once you know the names by placing the electrons in place of the atoms and then determining what that geometry is. All right, so what do we do with, I'm skipping all around here because I wanted to go to that table. So what we can do is use this to predict the structure of molecules that we might not know. In this example, we're reacting phosphorus gas with excess chlorine, forming phosphorus pentachloride. Then we make PCl4 plus and PCl6 minus ions. Let's predict the geometric structures. We just did PCl5, so we know that's going to be trigonal bipyramidal. But let's look at PCl4 and PCl6. We need to build the Lewis structures to figure out the structure, because without building Lewis structures, we don't know how many lone pairs are on that central atom, and so we don't know how many electron groups. So see if you can come up with structures for PCl4 plus and PCl6 minus, and then if you do that, draw the structure of xenon tetrafluoride, XeF4, and determine whether it has a dipole moment. So now that we can derive the structures, we can also add up the dipoles and determine if a molecule is overall polar or not.
Is lone pair of electrons affect polarity?
No, because it's on one atom entirely. So only in that it can distort the structure a little bit.
Okay, so you had like a square planar with 2 of the 4 elements on the outside being the same, and then 2 of the 4 being a different element.
Right.
Would that affect its polarity?
Depends how they're arranged. If the 2 that are the same are across from each other, then it would be nonpolar. If the 2 that are the same are next to each other, then it would be polar. So we may have different lines of vectors
to cancel out if they're just square.
Right. So you have to look at the vectors and see if they cancel out. All right, so what do we got? What's the shape of PCl? Well, okay, I'll put PCl5 because we did that. We know that that's trigonal bipyramidal. What about PCl4 plus? What does that come out to? What shape do you get for that? Right, so even though we reduce our chlorine by 1, we don't have a lone pair to put there. So that's why it's important to actually build the Lewis structure rather than just assuming or trying to guess. PCl4 ends up being a tetrahedral structure. And then PCl6 minus is octahedral. So trigonal bipyramidal, tetrahedral, and octahedral. And then xenon tetrafluoride, that's the one we just looked at, which is square planar. So if it's square planar, does it have a dipole moment? Let's try and see. All right, there's our square planar xenon tetrafluoride. What is the dipole moment? Or how do you calculate that? How do you figure it out? Right, we know there's a big electronegativity difference between xenon and fluoride, with fluoride being more electronegative, fluorine being more electronegative. So we have dipoles in all four directions of equal magnitude. Those are all going to cancel each other out. So the net dipole moment is going to be 0, no dipole moment overall in this molecule. Now, Trevor had a good question. What if this was like XeF2Cl2? There's actually two different structures for that type of a formula. There's this one. And there's this one. Those are not resonance forms. The name for those is stereoisomers. But anyway, they're two different structures. One of them has a dipole moment, and one of them does not. The one on the left does not have a dipole moment. We know fluorine's more electronegative than chlorine, so the XeF bonds are going to have stronger dipole moments than the XeCl bonds. In this case, they're right across from each other, so green cancels green and red cancels red. But in this example, they're not. So if we added up all these dipoles, we'd end up with an overall net dipole moment in this direction. So this side of the molecule would be more negative over, sorry, this side of the molecule by the fluorines would be more negative. This side would be more positive. And there would be an overall dipole moment. Now, could you tell which one was the correct structure based on just the formula XeF2Cl2? No, you'd need more information. But I could ask something like, I could say something like, this has two possible structures. The molecule was measured to have a dipole moment, so which is the correct structure? And then you'd know if it had a dipole moment, it would have to be that structure on the right. Okay, so let's try one more. And then we'll mess it up a little bit. Give the geometry of all electron pairs, so the electron pair geometry and the molecular and the structure, the shape of the atoms, the molecular geometry for I3-. We've looked at this triiodide ion before. Let's build the structure again, but this time let's also look at the geometry. See what you get. Got some geometry for this one yet? So you got a Lewis structure like this. Or did I do that wrong? 28 electrons total, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Or 22 electrons, yeah. So that's right, right? No double bonds or anything. That should be the correct structure. So what's the geometry? First, what's the electron geometry? The geometry of all the electron pairs together. What do you call that? How do you figure that out? What's the electron geometry? That's kind of like the big category that encompasses all the groups. What? Planar would be the structure, the molecular geometry. So the molecular geometry, or the shape, we would call it not planar, but linear, meaning that the atoms are just in a straight line. The electron geometry tells us something about how the electrons are distributed. So electron geometry includes both the lone pairs and the bonds. So if we count the lone pairs and the bonds, we have 1, 2, 3, 4, 5 around the central atom. So what shape is that? What? Nope. Tetrahedral is 4. 5 is, yeah, Trigonal Bipyramidal. So we have to be careful in determining the molecular geometry before the electron geometry, because in some cases, water, for instance, and other molecules like that, it still has 2 atoms attached to the central atom, but it's not linear, because those electrons take up some of that space as well. All right, so let's look at what happens when we get some multiple bonds. NO3, we've done the structure for NO3 before. We talked about it with resonance. We usually look at it something like this. What's the shape then of that molecule? What do we call that shape? How many groups of electrons are around the central atom? 3, if we're counting the double bond as 1 pair, which the text below says that we are. So the structure of this should really be trigonal planar. And we can measure that, and we see that indeed it is. Those bond angles in the nitrate ion are 120 degrees. This also gives us evidence that there's resonance going on here, that it's not actually a double bond and 2 single bonds, but rather an average throughout the molecule. The reason for that is that if it were a double bond and 2 single bonds, we would expect the double bond to repel a little bit more, just like a lone pair does, because of the more electron density. We'd expect there to be some uneven bond angles. So maybe instead of all 120 degrees, maybe 2 of them are a little bit bigger than 120, and then 1 of them is a little bit less than 120. But actually, they're all even. And that tells us that there's not a double bond and 2 single bonds, but rather 3 bonds that are averages that are like 1.5 or 1 1/3 bonds. So make sure when you have double bond molecules, you're only counting them as 1 group. All right, so to practice that, see if you can come up with a structure for the sulfur dioxide molecule, SO2. and then determine whether or not you expect it to have a dipole moment. Yeah.
So linear and linear don't need two shapes for the molecular geometry.
No, there are lots of different shapes. You've got trigonal planar, bent, tetrahedral, trigonal pyramidal, seesaw, T-shaped. All the shapes that the molecule could be in, if you're just counting the atoms, are the molecular geometry.
Okay, so that's the first one.
Okay. See if you can get sulfur dioxide. So what do you got? What's the structure? Who says it's linear? Bent? Those are the only two choices for two atoms on the central atom, right? You can either be linear or it can be bent. The only way we can tell is by building a Lewis structure and determining if there's lone pairs on the central atom or not. So we've got sulfur dioxide. We build it like this. We know it has 18 electrons. So that's 2, 4, 6, 8, 10, 12, 14, 16, 2, 4, 6, 8, 10, 12, 14, 16, 18. What's the problem there? Octet rule. So what do? Yeah, we got a double bond with one of these oxygens. So we take out a pair there and put it like that. Okay, so what does that tell us about the structure? Yeah, it's got to be bent, not linear, because our electron geometry tells us that there are 3 groups. 1 lone pair and 2 atoms. So if we have 1 lone pair and 2 atoms, that's 3 groups. That's trigonal planar. So we could draw this in a trigonal plane with the lone pair, the oxygen, the other oxygen. There's also formal charges here. If we really wanted to minimize formal charges, we could also make another double bond from the O to the S. So if we did that, there would be no formal charges. Notice that it doesn't change our electron geometry. So these resonance forms don't change the geometry. So that shape is trigonal planar, or that geometry is trigonal planar. If we just look at the atoms themselves and not the electron, we would call that bent. And that's why it's important to look at all the electron pair geometry before you determine the shape. It's not like, saying, I know carbon dioxide is linear, so sulfur dioxide must be linear too. It doesn't work like that. You got to look at the electrons and figure out what the shape's going to be. All right, what happens when there's not really a central atom? How do we determine the geometry? The answer is we sort of don't. And there are some questions about this on your exam. Organic molecules like this, molecules made of mostly carbon and hydrogen or carbon, hydrogen, and oxygen, are going to have multiple different centers of geometry. And what you can do is actually look to each one. So this structure, CH3OH, kind of gives you a clue as to what its structure is going to be. It tells you that the 3 carbons are around that, or the 3 hydrogens here are around that carbon. And then it kind of branches out from there. So we're going to put our carbon down with 3 hydrogens on it. We're going to connect it to the oxygen and then another hydrogen. The reason we know it has to be like that is because we can't put hydrogens in between. We know hydrogen only gets 1 bond. So the carbon and the oxygen must be in the middle. And now what we can do is determine the geometry for each central atom. So we'll determine the geometry for carbon. What will that be? What's the geometry there? How many groups are around that particular carbon atom? Just 4. So we've got the hydrogen, the oxygen, the hydrogen, the oxygen. 4 groups around that carbon. We would call that tetrahedral geometry. For the oxygen, how many groups are around there? Right, we've got 4 electron groups. 2 of those are lone pairs. So that tells us that this starts as a tetrahedral geometry. But the 2 atoms tell us that it would actually be bent. Just like water. So you've got an oxygen with 2 atoms connected, the C and the H, and then 2 lone pairs. So if we want to draw the structure a little bit more realistically, we might draw it in that 3-dimensional notation, showing that the hydrogens are not in a square plane like that, but rather are in a tetrahedral type shape. And so is the oxygen. The oxygen to the hydrogen bond, the COH angle is bent. So we would expect this angle to be about 110 from tetrahedral. We'd expect this angle to be just under 110 like water because of the lone pairs pushing it, but still based on that tetrahedral angle. What would we expect the bond angle to be in sulfur, in the sulfur dioxide here? Actually not in this case. We'd expect this to be about 120 because that angle is based off of the trigonal planar geometry, the 3 corners of a triangle geometry. And so you can have 2 shapes like bent that sound the same and kind of look the same, but actually have different bond angles because they come from different electron geometries. If we go back to our shape here and we look at SO2, there's our model with 120-degree bond angles as opposed to something like H2O, which has that more narrow bond angle. We should also see less of a distortion in the SO2, and we do just a degree if that, because we know that if they're already that far away, 120 degrees away, there's going to be less interference with that lone pair. So remember that the geometry, that is the bond angles, come from the electron geometry. That's where you're going to get your bond angles, even if the name of the geometry is the same. All right, so there's kind of this table that sums it all up. Tells you the electron groups, the bonding groups, and then based on the bonding groups versus the lone pairs, that is the atoms versus lone pairs, that's going to give us the molecular geometry. So you can practice those. Okay, let's move on and talk a little bit about hybridization. That was the last part of the lab, which we didn't quite get to. This idea of hybridization. So what does this mean? Let me draw you a picture. We say that methane looks like this. We've just been talking about that. It's this tetrahedral geometry where everything's all even like that. But if we think about the actual orbitals and the electrons involved, this really doesn't make a lot of sense. So think about what electrons are involved here. We've got 1s orbitals from the hydrogens. And then the carbon, the valence electrons are in the 2s and the 2p. So 2 electrons in the 2s, and then 1 electron in each of 2 different p orbitals. So I'm going to draw a really weird picture here that's going to try to take that into account. So here's our central carbon atom. And first we're going to say, all right, it's got 2 electrons in the 2s. So we know a 2s is a sphere. And we've got 2 electrons. Now we know that there's not orbits, of course, but we're going to pretend for the sake of this that we've got 1 electron kind of on each side of this. And those are bonding with the hydrogen orbitals, which are also 1s orbitals. So we've got, let's see, I hope I have enough colors here. We have a hydrogen 1s orbital there, and a hydrogen 1s orbital there with its electron. And the carbon's bonding to those 2 hydrogen 1s. Okay. So then the other, if we say that those 2s electrons are bonding with 2 of the hydrogens, then the other 2 hydrogens must be bonding with the 2p. See where I'm going with that? Because that's the 2 remaining orbitals. 2p, if you remember, has that dumbbell shape and stretches out a little bit past the 2s. So I'm going to draw this the 2p in red. So one of them kind of looks like this, and the other one kind of looks like this. So we'll say there's a little electron here and an electron here. And 2 p orbitals are orthogonal to each other. They're perpendicular, 90 degrees. So then our last hydrogens go like this with their electrons, and those are, again, the 1s orbitals from the hydrogens. This picture's getting pretty messy. Okay. Hopefully what you can see from that is not the correct picture of a methane molecule. If we go back to our normal lines for bonds, what we've said is that this means that there is going to be 2 long bonds from the 1s to 2p interaction, because 2p's are further away. 2 shorter bonds from the 1s to 2s, and all the bond angles are 90 degrees because the orbitals in the molecule are all orthogonal to each other. So if we look at the actual electrons in the valence orbitals, we come up with a picture that doesn't look like what methane actually looks like. And so that means we have to change our theory. It's not, we have to say, well, okay, maybe it's not the individual orbitals that are bonding. Maybe they're actually coming together in a hybrid way, and we call that hybridizing. So rather than having discrete individual s and p orbitals doing the bonding, we're going to put the s and p together and talk about bonding with hybrid orbitals, but orbitals that are made part from the 2s and part from the 2p. And it looks like this. I just took a picture here from the book because I didn't want to try to draw it. We take an s orbital, which is the sphere, and we mix it with 3 different p orbitals. And the p orbitals are going in all orthogonal directions, perpendicular directions. So you've got one along the z-axis, one along the y-axis, one along the x-axis. If we think about the s orbital combining with those, we get these kind of weird-looking things. This is probably the best picture of it here, where it's kind of like a p orbital with one big lobe and one little lobe. And we call that an sp3 hybrid orbital. That name comes from one s orbital combining with 3 p orbitals. And we make 4 hybrid orbitals that are pointing into the different sections of the triangle. Now, if you don't believe me on this, that's fine. You can dig into the math on it. If you actually model those shapes and you make linear combinations of them, that is, you add and subtract them from each other, this is indeed what you come up with. You come up with these different 3-dimensional shapes that point to the different corners of the tetrahedron. So if we put all those together, these hybrid combined orbitals actually give us the correct picture of what we see. So the theory then becomes, well, if these things combine to hybridize, maybe we can predict the bonding behavior based on that. So each hybrid orbital now is going to have 1 electron in it. So we took the 4 valence electrons, instead of being 2 in the 2s and 2 in the 2p, we hybridize them all together, and we put 1 electron in each hybrid orbital. And then each of those is going to combine with that hydrogen 1s orbital to make the bonding picture. And that is the correct bonding picture that we see for methane right here. So what do you think about that? Sense? Confusing? Weird? What? That was a lot. Okay. So let's talk about why that happens. It's an energy thing, as most of this is. It's driven by energy. If we think of the standard atomic orbitals, the 2s underneath, the 2p on top, 2 electrons in the 2s, 2 electrons in the 2p, if we instead make 4 hybrid orbitals, we've overall decreased the energy of the system. So the overall system of hybrid orbitals is more stable. And that's kind of the driving force to create them. The good news is you don't really need all of this stuff to accurately predict the hybridization. The hybridization can be predicted from the electron geometry, just as the shapes can and the bond angles can. Let me show you what that looks like. Ammonia. The ammonia molecule is NH3. So we draw this type of a picture of it. And then we want to know the molecular geometry. So what do we do to find that? What's the first thing we do once we've got our Lewis structure? Yeah, number of groups. So how many electron groups does it have? 4. 3 hydrogens and the lone pair. 4 electron groups. And that tells us that it's going to be tetrahedral bond angles. So this kind of a shape. And then since we don't see the lone pair, we get rid of that. And do you remember what that shape is called? You have 1 lone pair from a tetrahedral shape. You may remember the name of that from the table. I'll give you a hint. It's kind of a triangle, but it's not planar. So what's the other triangle that's not planar? Yeah. So instead of trigonal planar, we call that trigonal pyramidal. Okay, so we got that so far. What's nice about the hybridization is the hybridization can also be predicted from the electron groups. So not only can we tell that this is tetrahedral, but we can also tell that this is sp3 hybridized. How do we know? Well, we can add up the numbers in our hybridization. So we've got 1 from the s and 3 from the p. gives us 4 hybrid orbitals. If you have 4 hybrid orbitals and they're all repelling each other, you end up with a tetrahedral structure. So any tetrahedral electron geometry, whether it's in methane or in ammonia or in water, is going to lead to sp3 hybridization. Those 4 electron groups are always going to tell us that it's sp3 hybridization. We need 4 hybrid orbitals to get 4 electron groups. 1 hybrid orbital contains the lone pair. The other 3 hybrid orbitals point to the other atoms. So if we describe the bonding in this structure, what we might do, we can draw it actually. We can take our nitrogen, and now instead of drawing s and p orbitals, we're going to draw hybrid orbitals. It's always tough to draw these in 3D, but remember the hybrid orbitals have a big lobe and a little lobe. And the sp3 hybrid orbitals are all going to be pointing out toward the hydrogens. And then there's going to be a 4th one that contains that lone pair. The hydrogens are bonding with their s orbitals. And that is a picture of what the bonding looks like. These bonds would be sp3 1s bonds. So an sp3 hybrid orbital bonding with a hydrogen 1s orbital. And then you have one leftover sp3 orbital that contains the lone electron pair. If we use individual s and p orbitals on that nitrogen, we wouldn't get the correct shape. And so we need to use our electron groups to determine the hybridization. Okay. Let's look at some other types of hybridization. Again, these are also going to come from the electron group. So before we even get into it, if you're going to predict sp2 hybridization, I didn't tell you anything about what it is, but what shape do you think sp2 hybridization might work with? If sp3 is for tetrahedral, what do you think sp2 is for?
Triangle.
Yeah, triangle planar or trigonal planar. Right. So when we have 3 electron groups, we use sp2 hybridization. Right? 1 s orbital and 2 p orbitals hybridize. That's what happens in this molecule CH2O, which is formaldehyde. The structure looks like this. Three electron groups tells us that it's trigonal planar. And it also tells us that we need 3 hybrid orbitals, 1 in each direction, to get those correct bond angles. So that bond angle is going to be 120 degrees. And so now we're talking about an s orbital combining with 2 p orbitals to form 3 hybrid orbitals. So notice now that s orbital, based on the axes that were chosen here, the s orbital is combining with the px, the p along the x-axis, and the py, the p along the y-axis. And those combinations give you 3 orbitals pointing in each direction, but you'll notice none of them are pointing on the z-axis at all. Nothing's pointing out at you or going back. And that's because we are not combining with that 3rd p orbital. So we don't get that 3rd dimension in our hybrid orbitals. We only get the 2 dimensions. So what happens to that 3rd orbital? That 3rd p orbital that's unhybridized. It just sits there. It's just there. It's not hybridized. So when we want to describe the bonding in CH2O, we have something else going on here. Because it's planar, I'm actually going to tip this thing kind of on its side so we can look at it edge on. So here are our 3 sp3 hybrid orbitals. Or sp2 hybrid orbitals. And these are going to be in this trigonal plane here. And that leaves behind one unhybridized p orbital going in the other direction. So that's a p orbital that's not hybridized, not combined with the s's. So we have our 3 hybrid orbitals and then 1 p orbital that is not hybridized. The way this bonding works then is that the 2 hydrogens are going to go with their 1s orbitals over here. And then we don't usually think about it this way. It doesn't necessarily make a whole lot of sense. But we can also determine the geometry of this oxygen atom. Even though there's only one thing connected, what's the electron geometry of that oxygen atom? How many electron groups are there on it? Well, there's one bond, one atom connected, but how many if we include the lone pairs? 3. So we might say that that oxygen is also sp2 hybridized. So the oxygen is also going to have, an sp2, 3 sp2 orbitals. Two of which contain these lone pairs. And then it will also have an unhybridized p orbital. And we're going to get into what happens between those 2 p orbitals in a little bit. But that's how valence bond theory describes what's going on in CH2O. Is it says that there are these 3 hybrid orbitals formed from the s and 2 p's. Those form the main structure of the molecule there, and then there are these 2 leftover p orbitals. Those 2 left, I guess I'll just tell you the answer before we get there. But the 2 leftover p orbitals are actually going to share electrons as well, because they're lined up like that. And that's what's known as a pi bond. Yeah.
Why is there 2 other p orbitals?
Where?
Why is there 2?
Oh, each p orbital has 2 lobes, has 2 parts.
So like the other one is supposed to be.
No, a p orbital has 2 equal sized lobes. The hybrid orbitals have a big and a small lobe.
Oh, okay.
Yeah.
Because you're not hybridized.
Right. So these are not hybridized, so they stay like that. All right, we'll go through the rest of our hybridization, and then we'll probably save the rest for next time. So we can also do this in a couple of different ways. We can keep going down and say sp, meaning only one s and one p get hybridized, and you end up with 2 unhybridized p orbitals. As you might imagine, this is going to be used in linear compounds. So compounds that only have 2 groups are going to be sp hybridized, only 2 electron groups. And that leaves 2 not unhybridized p orbitals. So we see this example in the N2 molecule. Let's draw a Lewis structure for N2. We've seen this many times before. But you have something like this. Now, normally we wouldn't worry about the geometry of an N2 molecule because it's just obviously linear. There's only 2 things. But we can say each nitrogen atom actually has 2 electron groups on it. Do you see that? Each nitrogen it's bonded to an atom, and then it also has a lone pair. So we can look at those as being hybridized, and we can talk about those as having 2 hybrid orbitals. So each nitrogen, make this bigger, maybe it'll be a little bit clearer, is going to have 2 hybrid orbitals, sp orbitals. So there's the sp going one way, and then there's another one going the other way. Same thing with the other nitrogen. sp, sp. So that lone pair is going to be in this outer hybrid orbital. That also means that each nitrogen has 2 leftover unhybridized p orbitals. So one of them looks like this on each. And then the other one is perpendicular to that one, but not in line with the hybrid orbitals. So it's going to be hard to draw, but it's coming out at you and going back like that. And so the triple bond in nitrogen comes from, the first bond is the 2 sp orbitals overlapping. That's called a sigma bond. The second bond is from one of the pairs of p orbitals overlapping. Even though it has 2 parts, that's considered one bond. And then the third bond is from the last set of unhybridized p orbitals interacting. We'll get into these next time, but an interaction like this one where they're the 2 orbitals are kind of smushed together, that's called a sigma bond. And these other 2 types of interactions are called pi bonds. A sigma bond is where the 2 orbitals just kind of smush together. A pi bond is where you have two p orbitals that line up and interact both on the top and on the bottom. So that's the 3 bonds in the nitrogen triple bond. One comes from the interaction of the 2 hybrid orbitals. The other 2 come from the the unhybridized p orbitals combining together. And that's about as complicated as it gets with this hybridization model. The other 2 types of hybridization involve the d orbitals. And this is how we can violate that octet rule. We mentioned about how things below the second row can violate the octet rule. It's because their d orbitals can hybridize with the s and the p to give us more possible orbitals to bond with. So we talked about PCl5 a few times today. None of the sp, sp2, sp3 hybridization modes account for this because we need 5 hybrid orbitals. We've got 5 electron groups, we need 5 hybrid orbitals. So instead, we talk about dsp3 hybridization, or in some groups, it's known as sp3d. I can't remember which one this particular book uses for that. They call it sp3d, so we'll stick with that. Same thing, but now you can count, again, the orbitals in the hybridization. You've got 1s, 3p, 3 from the p, and 1 from the d. That's 5 total orbitals combining to make 5 hybrid orbitals. So here's a picture of that. 5 orbitals combining to make 5 hybrid orbitals. We saw the triiodide ion earlier. Go back to draw it again. We said that its electron geometry was trigonal bipyramidal. And so that tells us that we need 5 groups for 5 electron groups, and therefore its hybridization is sp3d. So hybridization goes with electron groups always. And then the last one is sp3d2, or d2sp3. How many effective pairs do you need for that, you think? For sp3d2? 6, right? 1 from the s, 3 from the p, 2 from the d, 6 pairs. And that's what we get in our octahedral coordination or octahedral bonding. Oh, something's going on with the computer here. It doesn't like that. Okay. 6 electron groups here. So we need 6 hybrid orbitals. So the take home on this is that even though the hybridization stuff gets kind of tricky to think about and how these things are hybridizing, and that's fine, and we can get into it more, but the important thing to think about or to realize is that you can always determine the hybridization just by looking at the number of electron groups. It's good to understand what's going on and where the hybridization comes from and why and all that stuff. That's great. But in order to determine the hybridization, all you need is the number of electron groups. And you use a hybridization that fits for the number of electron groups. So there you go. You can draw the Lewis structure. You can determine the arrangement of the electron pairs, determine the electron geometry. And then you'll know the hybrid orbitals needed to accommodate that many pairs. Whether they're bonds, whether they're lone pairs, doesn't matter. Once you have the number of electron groups, you also have the hybridization. All right, so last thing to sum up, draw a Lewis structure for each of these 3. Determine the hybridization and describe the molecular structure. What shape is it? If you can do that for these 3, then you're all set with this stuff. Not that these 3 are super hard, but it's a general, like this is an example. Yeah.
In the lab, you have one that's SO2, CL2.
Mm-hmm.
It goes back to like square plane.
Right.
How would you know which way that's supposed to go?
If it's not specified, you don't.
So, what are we supposed to write down in the plan?
Do it however you want, and then answer the dipole question based on what you wrote down.
Right.
Actually, it's SO2CL2.
Yeah, where is that wrong?
Yeah.
G, SO2, CL2.
Because that should be.
Maybe I did the structure wrong.
No, I'm just thinking about it. It might be one of those. It may be one that where. Are you sure it turns out square planar?
I mean,
According to the number of electrons you got.
CL2, 14 years.
So you that it is. Yeah, so that's not going to be square planar. And so what it ends up being actually means that there's only one possible. Remember when you draw these Lewis structures now, to be a little bit more careful about them and make sure you're drawing the best Lewis structures with the fewest formal charges. That's going to influence the hybridization. What do you get for Lewis structure for CO? So you want to describe it to me? A triple bond between carbon and oxygen. Okay, just like that. Done.
Well, no, okay, with the electrons on, 2 electrons on carbon.
Okay, 2 on carbon, 2 on oxygen. Done. Good structure. What are we missing? Formal charges. So this structure actually has a negative charge on the carbon and a positive charge on the oxygen. All right, make sure to include that. The overall charge is neutral, but we got to make sure to have our formal charges. Okay, what about hybridization? What do we think of hybridization for carbon and for oxygen here? There's no central atom, but we can still talk about the number of electron groups for each atom and determine a hybridization. So what's the hybridization of carbon here? Yeah, sp, 2 electron groups, 2 hybrid orbitals, and the same for oxygen, just like N2, just like nitrogen. All right, I've lost control of my mouse here. Must be running out of memory. So BF4, hopefully you came up with something like this. How would we describe that molecular structure? What shape is that? Yeah, it's tetrahedral. 4 groups around the central atom. Now, when you first write down the Lewis structure, you may not write it like that. You may write it, normal kind of T-shaped looking. But once you discover that there are 4 electron groups and it should be tetrahedral, then you should redraw it to reflect its molecular structure like this. So then what's the hybridization on that central boron atom? How many electron groups? 4. So what are the hybrid orbitals that give us 4 groups? sp3, right? And we can count it right on there. 1 from the S and 3 from the P. All right, finally, xenon difluoride. What kind of a structure did you get for this one? sp3d. How'd you come up with that? Like this? Yeah. Okay. So then we've got 5 groups around the xenon, which tells us the electron geometry is trigonal bipyramidal, and therefore the xenon must be sp3 dehybridized. And how would you describe the molecular structure? The overall structure is, what about the molecular shape of just looking at that shape? Is it linear like we've drawn it, or should it be bent? Why bent? Okay. More electrons on top than bottom. Other thoughts? Agree, disagree? we can figure this out by going back to that original structure. If it's trigonal bipyramidal, that means that we've got a xenon in the middle with 5 bonds coming off of it like that. So we want to distribute this so that the 3 pairs of electrons are as far away from each other as possible. And the way to do that is to put them all on the corners of this triangle. That leaves the 2 fluorines on the axial positions. And so that that gives us ultimately a linear structure. If there were only 4 groups, like in water, then the 2 electrons would be farthest apart from each other by going on the 2 corners of the tetrahedron, leaving the other 2 hydrogens there. All right, so that is called valence bond theory. Valence bond theory, this idea that these orbitals hybridize, and that's what leads to these shapes. Valence bond theory works very well for some of these smaller molecules, and then we'll see some examples where it breaks down. It breaks down when we have odd numbers of electrons, and it breaks down in some cases where the molecule really, well, it doesn't do a good job of telling us things like whether or not there should be double bonds or triple bonds. Sometimes we have to think of other ways to do that. So on Thursday, we're going to look at the other big theory about bonding called molecular orbital theory, and look at a different picture of how electrons work together to form molecules. So lab tomorrow, last one. Don't try not to cry or anything, or make sad. And then we will go on from there.